So, today's chapter, we are going to read about energy and forces. Now, the energy we will be talking about is, just a minute. Now, have you ever wondered how a telescope works? Now, today you're going to learn it. You know already what is a telescope, right? I'll just read a simple introduction. Powerful telescopes make faint objects such as distant stars and galaxies easier to see. They work by first gathering as much as light as they can using either a lens or a mirror, and then focusing the light into a clear image. There are two main types of telescope: refracting, which focus light using lenses; reflecting, which focus light using mirrors. Optical telescopes see visible light, but telescopes can also look for different kinds of electromagnetic radiation. Radio telescopes receive radio waves, and X-ray telescopes image X-ray sources. Telescopes use large lenses compared to microscopes, which are used to look at things incredibly close up, while binoculars work like two mini telescopes side by side. So, we are going to see about the parts of a telescope. First is the eyepiece. A viewer looks through the eyepiece to see a clear, focused image of the distant object. A magnifying lens focuses and enlarges the image. So, right. You can see this is a telescope, right? A telescope. Then is the first surface mirror. A mirror reflects light at right angles into the eyepiece. I'm sure at the bottom of the page you can see this method, right? It's basically the explanation of convex and concave lenses. It's like the lens. Pretend my hand is a lens, and right through my hand is the principal axis that focuses on light. Then over here on down is the ray of light. Then at the other end here, the convex lens, the ray of light, converge. They converge the light rays. And then at the end there is a simple dot. That's the principal focus. Then it focuses on all the light in front. That's the explanation of a convex lens. Now concave lens. It's almost the same, the principal axis. But down is the virtual rays, and up is the ray of light. Then the ray of light at the other end goes up, focusing up. They diverge, and then the principal axis straight, and the virtual rays, they go down, converging. Fun fact: Isaac Newton created the first reflecting telescopes to get around the problem of color distortion. Then the focus knob. Twisting the knob adjusts the focal length to focus the image. Then comes the refocus lens. A second lens refocuses the light after it has passed through the filters. I mean here, right here, you can see this lens, right? That is the refocus lens. Then the filters, that is here on the top, here. Telescopes may use a variety of filters to get rid of specific wavelengths of light. Then is the collimating lens. That is right in the front of the refocus lens. This lens refracts the light into a parallel beam to pass through any filters. Objective lens, that is straight at the end of the telescope. Here, at the end of the telescope. Objective lens. Light from a source hits this large convex lens, which I just told about, the convex lens and the concave lens. Light from a source hits this large convex lens, which focuses it. Got it? Next, I'm going to tell you about the rainbow effect. That is also related to the telescope. When white light passes through a glass lens, it is refracted, creating a rainbow of colors around the image, an effect known as chromatic aberration. Modern telescopes use extra lenses to counteract this. So, at the starting, red, green, and blue light focus at different points. Some go up, some go down. Straight through is the optical axis. Then this lens splits white colors into colors. The optical axis is where we see on. Next, we will be talking about magnetism. I'm sure we'll read one more page after this, but stick around for more. Okay, you know that Earth has its own magnetic field. I'll show you. Here. We see it here. I'm sure you saw it. Now, first at the bottom where the magnetic see, I'll tell you how poles attract. Unlike poles attract, like poles repel. Unlike poles attract, like poles repel. The invisible field of force around the magnet is called a magnetic field. You know when you try to press the two together north poles together, and there's a force that just pushes them. That is the magnetic field. The invisible field. Wait. Iron fillings show how the magnetic field loops around the magnet from pole to pole. Attraction. When you join the north and south poles, it connects, right? Unlike or opposite poles, a north pole and a south pole attract each other. Iron fillings reveal the lines of force running between unlike poles. Repulsion. Like poles, two north or two south poles repel each other. Iron fillings show the lines of force repelled between like poles. Now, have you seen compasses? compass. And have you ever wondered how they actually work? Now today I'm gonna explain you. Here you go. Made of magnetized metal and mounted so that it can spin freely, the needle of a magnetic compass lines up in a north or south direction. In Earth's magnetic field, because the Earth's magnetic north pole attracts the north or north-seeking pole of other magnets, it is in reality the south pole of our planet's the Earth's magnetic north pole attracts the north or north-seeking pole of other magnets. It is in reality the south pole of our planet's magnetic field. Now, I'll tell you how the Earth's magnetic field protects us from the sun's deadly rays. A teardrop-shaped magnetic field. Earth's magnetic field protects us from the harmful effects of solar radiation. In turn, a stream of electrically charged particles from the sun, known as the solar wind, distorts the magnetic field into a teardrop shape and causes the auroras, displays of light around the poles. Okay, I don't know if we'll have more time, but we'll go on to page 90 to 91 for seeing more about the teardrop shaped magnetic field. Now, have you ever heard about the northern lights? Aurora borealis? Now I'll tell you, it's because of the Earth's magnetic field. When the sun produces deadly radiation, our Earth's magnetic field just sends it away. Like, the spectacular natural light shown known as the Aurora borealis or northern lights is a dazzling spectacle of ribbons and sheets of yellow, green and pink light. The cause of the aurora is this stream of charged particles ejected from the surface of the sun, known as the solar wind. These particles are guided toward the poles by Earth's magnetic field. When they hit oxygen and nitrogen molecules in the atmosphere, electrons in the molecules emit colored light. The northern lights and aurora australis or southern lights around the south pole occur whenever the solar wind blows, typically about 200 nights a year. Isn't that fascinating? Okay, I think this is enough for today, but stick around to my channel for more because we'll be posting. Thank you. Have a great day.